For high school chemistry, this is Unit 4, and this is the last section of Unit 4. And we'll start off talking again about the atomic number. We ended with the atomic number, so you're on capital letter E, atomic number. And again, this is the number of protons in the nucleus of an atom. On the periodic table, it's the nice large whole number. It may be in different periodic tables are going to be set up in different ways. It may be on top of the symbol, it may be below the symbol, it may be to the right-hand corner, who knows. You just have to look at each periodic table. Most periodic tables will have a key, and they'll label where the atomic number is and the mass number is on that. The only thing that makes one element different from another is the number of protons in the nucleus. That's it. That's what gives everything their characteristics. So that's what makes gold different from oxygen or different from carbon. It's how many protons are in the nucleus of the atom. So the number of protons are really, really, really important. And you should be on page 3 of your notes. Oh yeah, page 3. So you're writing down this whole long letter A. So I'm going to sit here and make up crap to say so that you can write this down. Oh my gosh. So the only thing which makes one element different from another is the number of protons it contains. If you need to pause this or go back, feel free, and you can hear it twice. An atom with 6 protons is always, 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 always carbon. An atom with 5 protons is always, 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 always boron. And an atom with 7 protons is always nitrogen. It doesn't matter how many electrons or how many neutrons, number of protons tells you what it is. Now, the mass number is also called the atomic mass, or the atomic mass number, is the sum. Sum means you're going to add of the protons and the neutrons in the nucleus of an individual atom. So the mass number, to get the mass number, you add protons and neutrons. The average mass number for each element is on the periodic table, not the individual mass number. So you're going to find that you don't have a nice whole number like, oh, there are 6 protons and 6 neutrons. You don't have that. You have, where the number's 12, you have like, 12 point something or other. So it's the average mass that's on the periodic table. The mass number for an individual atom is not on the periodic table. Right. Mass number is equal to the protons plus the neutrons. And so I'm just kind of repeating this. You'd think you hear it multiple times. The mass number, if you're looking for the actual mass number, it's always a whole number, and that's not on the periodic table. The average mass number is on the periodic table. Think of it as your average for your grade in chemistry. It's not one perfect grade where it's exactly an 81. It's going to be an 81 point something or other, and we round it because it's an average. On the periodic table, you have an average, and they're showing the digits to the right of the decimal. So it's not an actual mass number for one atom. It's the average. Okay. The average mass number is the mass number that shows on the periodic table for each element. And it's really something called a weighted average mass. And what that means is it's kind of like your chemistry grade. 40% of your grade would be the test papers and 25% would be the labs. They don't count for the same amount. So we say it's weighted. Now, lucky for us, on our grade books, the computer does all the math for us, so we don't have to worry about it too much. It just takes less time for us to do it now. But you're going to have to calculate the weighted average mass of the isotope. That's what the state of Texas says. You have to calculate the average masses. So it's weighted some way more than that. It's kind of like saying, well, you can have carbon-12 and you can have carbon-14, but carbon-12 is much more common. So, let's say 70% of all the atoms of carbon are going to be carbon-12. So we should count that more than what we count the carbon-14. It should count for more. So here we have helium. Helium has an atomic number of 2. It's the green one on top. And it has an average mass number of 4.003. It doesn't mean that you have 4.003 protons and neutrons. You can't have 0.003 of a neutron or a proton. It means that you have 2 protons, and on average, helium atoms have a mass of 4.003. So let's round that. So the most common number of neutrons that you have will be 2, because 2 plus 2 is 4. If we round that 4.003, if we just round it to a whole number, it's 4. So we have 2 neutrons, 2 protons, and that's what normal is there, the average one. Okay, so we have the symbol, and then we have the atomic number at the top that tells us the number of protons. And I think instead of letter B there, it should be number 2 on that one. So if you're off a little bit, it's, I think, the last, right above the Roman numeral number 2, that's where this goes in. So it's really an average of the masses of all the isotopes of that element. Okay, so when we do the average mass, how do we get that? Because this is what you're going to have to calculate. We have a lab, and we'll use that. We'll find the average mass of a new and strange element called runthium. It's the weighted average mass of all the isotopes on the periodic table, and it's rounded. Typically what I'll tell you to do is round to 2 decimal places when we calculate it. So you take the mass times the percent abundance, and plus the second mass times the second percent of abundance, and it's all divided by 100. It looks ugly, but it's not bad at all. Okay, so calculate the average mass number of oxygen if its abundance in nature is 99.76% O16 and 0.04% O17 and 0.2% O18. So we'd have the first one is oxygen 16, the mass is 16, and the percent abundance is 99.76, plus we have the next one is oxygen 17, O17, and its percent abundance is 0.04. And then we have the third one up there, which has a mass of 18, and its abundance is 0.2%. And then to get rid of all those percents, we just divide the whole thing by 100. So you punch all this into your calculator, and you come out with an average mass of 16.00. And this particular one is in atomic mass units. We could also, instead of doing AMUs, that's that weird unit of mass for pieces that are so small because of the atom is so small that they had to make up something to measure it in. We could also, instead of doing AMUs, we could say grams per mole. So if we had a mole of oxygen, then it would weigh 16 grams. Okay, now Roman numeral number 3 is what it should say on your notes, I'm thinking. Let me check. Did I just get that wrong? Roman numeral number 1. And, nope, it should be on the notes here. It should be Roman numeral number 2. I just got a little carried away. There are some people that you need to know. And the first one is Antoine Lavoisier. I'm sure there's a better way to say that with a French accent, but that's my best. So you need to write down that he is the father of chemistry. He was the first guy to actually do chemistry experiments. That's what you need to write down about this man. So that first little sentence there, he's a French chemist, father of chemistry, he was the first to actually do experiments, that's what you need to write down on your paper. In one experiment, and this is really, really pretty amazing, he weighed the reactants, like 2 chemicals, you put them together, those are called reactants, and then he collected everything that was produced, and he weighed the products, and he found that, oh my gosh, the mass didn't change. That's the law of conservation of mass. However many grams you start out with, that's how many grams you end up with. They may not look the same, but the mass, you haven't lost atoms out of the universe anywhere. So Lavoisier actually came up with the law of conservation of mass. If you need to pause this so you can write this down, you can always do that. Keep that in mind. Next guy, he's kind of a sad story. This guy, Henry Moseley, he discovered the atomic number of most of the elements that were known at the time. And you use this doing this whole X-ray diffraction stuff. And his name is really, he was barely out of high school. He was like 20 years old. So he did all this amazing stuff before he was even 21 years old. And his name isn't a household name like Einstein or any of those guys because he enlisted in the army. He went into World War I and he died. I mean, he was killed in World War I. And to this day, Britain doesn't require military service for their scientists because, you know, if this kid did all this, I mean, before he was even 25, I mean, can you imagine what he could have done later in life? I mean, it's just incredible, and it's sad that he's not here with us anymore. Okay, next guy on your list is Max Planck. Max Planck, and there's something called Planck's constant. Max Planck was a German physicist that came up with the quantum mechanical model of the atom, and that's what we believe is true today. Now, what he did is he realized that electrons don't actually orbit in perfect little orbits. there's actually kind of this area, this fuzzy area where you can find the electrons. And so they're in an energy, they're in a certain level around. So the electrons that are closest to the nucleus, that are orbiting around the nucleus in closest form, they're the ones with the least amount of energy. Then you have electrons that are farther out and they have more energy. But Max Planck is the guy that said, hey, I don't think they're going to orbit, these electrons are going to orbit in perfect little models like the planets orbit around the sun. It's a little less perfect than that. And we call that the quantum mechanical model of the atom. And we'll talk about that in the next unit quite a bit. Now you notice there's a lovely picture of a proton-neutron drawing on page 4 on your notes, where you can have the proton, the neutron, and electron, and we'll work on those in class. Right. And the last thing you have on there, the very last page of your notes, has some things that you need to remember, and that's just physical and chemical changes. You need to remember the phase changes are always physical. Freezing, melting, boiling, evaporating. Sublimating. Sublimating, it means it goes directly from a solid to a gas. And deposition goes back from a gas straight down to a solid. Condensing is physical. Tearing, crushing, heating is usually physical. All those things are physical changes because you haven't really changed the chemical that you're working with. Chemical changes, you're going to create some really wild new substance. If you burn it, it's going to be a chemical change. Cooking it, again, cooking a lot of times, not just heating it up, but cooking it, we usually end up having a chemical change. Rusting of metal, tarnishing of silver, anything that produces a new substance. Usually if it's bubbling and you've got some wild color change going on, those are going to be evidences of a chemical reaction. Don't ever forget that. And thus, we end Unit 4 notes. Now, let me just give you one more little hint here. For those of you who are doing what you're supposed to be doing and actually listening to the notes, taking the time and going through and writing the notes down and listening to it, here is an answer to a bonus question that will be on your next test. Are you ready? And you can write this down. If you'll take your notes and just turn up one little bitty corner of the last page, and yours might look a little bit different. Just turn up one little bitty corner so you have a little hidden thing right here. Here's the question, the bonus question, 5 points on your next test. Ready? How many kilograms can a human hair support? Like if you take one human hair and hang weights on it, how much can it hold? It can hold 3 kilograms of mass. That's just amazing. One little human hair, 3 kilograms of mass. Remember, 1 gram is about a paperclip, and a kilogram is 1,000 grams, so it can hold like 3,000 paperclips. Now, that's not for damaged hair. That's just for nice, normal, healthy hair. 1 hair can do that. It would be interesting to see if it actually held all that, because that sounds like quite a bit. But the answer to the question is 3 kilograms. Don't forget that. 5 points on your next test. Remember the unit of measurement, 3 kilograms. And have a good evening.